Hi everyone. You've been asked to do this worksheet, and hopefully you've done this worksheet, and now I'm going to show you how to solve these problems after you've tried. I'd like you to try this first and then see what I'm doing. By now you should be able to put these together after seeing the last video that I did for you where I showed you how to use LOL diagrams. Okay, so here goes. In this first problem, we've spilled a little water, and now that water is going to evaporate. So this liquid water is turning into gas water. We're going through a phase change. There's nothing in this problem that says the temperature has changed at all. So what we're going to do is keep the temperature the same. In other words, we're going to have thermal energy stay the same. All right, so we're at room temperature water, basically. So we're sticking to our prior rule that says we're going to use 2 bars to show that we've got liquid water at room temperature, okay? And that temperature is not changing for that water, okay? We've got room temperature water that's becoming room temperature vapor, okay? So the energy, thermal energy, is not changing. But we are going from a liquid to a gas, all right? Now, if we stick to our rule that was stated in the PowerPoint, we're going to start with 2 bars of energy for the phase energy, okay? That's liquid water. And we're going to increase that to 4 bars of energy, okay? All right, now you can see that there's a difference here, right? We're adding 2 bars of energy to the system, all right? This water vapor has absorbed some energy in order to go through the phase change. The temperature itself has not changed, okay? So we can see that energy is going into our system to make that happen. So in the process, our system gained 2 bars of energy, okay? We went from liquid to gas. The temperature did not change. So when you're thinking through these, think about what you're starting with and what you're ending with and what had to happen in order for that to happen. Okay, in this case, we started with a system that did not change in temperature. So ETH is the same in both cases. We used 2 bars of energy to show ETH because we're just going to use 2 bars to show room temperature. That's what we're going to try to stick to every time. And the phase energy increased because we know that in order to take a liquid to a gas, we have to separate those particles. Separating those particles it requires energy, okay? So that means we added 2 bars of energy. All right, let's try another one. All right, problem number 2 says, water vapor in the room condenses on a cold surface. All right, now, in order to understand what's going on here, I'm going to draw a particle diagram, okay? On my diagram here, I've got a cold surface right here, okay? It says cold surface. Outside of the surface, I've got water vapor, okay? So this is air right here, and this is the water vapor that's in the air, okay? Okay, and now I've got another diagram showing the same cold surface, and outside of that surface, we've still got air there. I haven't drawn anything for the air, but you can see how the water gas turned into liquid water, okay? All right, And we're also going to assume that, in fact, I should have wrote this. I'm going to assume that this is warm air on the outside. It doesn't say that in the problem, but just, follow what I'm saying. We have warm air in the end, okay? But during this process, we went from gas, water vapor, to liquid water. Okay, so what's happening to the water? The system is the water. What's happening to this water vapor to turn into liquid water? Okay, let's just talk through this right now. We've got a phase change going on, right? This is high phase energy, okay, because, a vapor or a gas has more phase energy to it than liquid substances. All right, so we're going from a gas phase to a liquid phase. That's a reduction in phase energy. Okay, and also we've got warm water vapor on this side, and while that water vapor, after it condensed, it becomes water. And now that it's connected to this cold surface, it's clinging to this cold surface, it's going to become cold. So we've got a couple of things happening here. All right, so I just wrote this here. The energy of phase is going down, and the temperature is going down. Thermal energy is going down. Okay, let's go back to the problem now. I wanted to start with this diagram so that we could visualize what's happening. It's always helpful to draw a diagram to help visualize what's going on. Okay, so now we're just going to follow the rules that we've already established for how we're going to fill in this bar chart. Okay, so we're starting at room temperature water vapor. So room temperature, ETH, that's going to be 2 bars, okay? And we've got water vapor. And if we follow the rules that we established about our bar charts, we're going to have EPH to be 4 bars, okay? And in the end, we decided that the liquid water is going to become colder because it's now attached to that cold surface, right? So ETH is now less than it was, and EPH is now at liquid. And we said before that we would say EPH of 2 bars means liquid. And of course, we're ignoring ECH. It's just not playing into any of this. So in order to go from the initial to the final, what did we lose as far as our diagram says? We lost 3 bars of energy to make that happen. So energy is leaving the system. That's our Q. Okay? And we're losing 3 bars of energy. So that is 3 bars of energy. Okay, so that's just redrawn there. All right, let's try another one. All right, in this problem, we've got a pan of water. It's at 25 degrees Celsius. It's heated to boiling, and some of the water is boiled away. Do separate energy bar charts for each stage of the process. So to start out with, like I said, sometimes it's helpful to have a diagram. I drew a pan of water. See what I did there? Isn't that a nice pan? There's my pan of water at 25 degrees Celsius. Now we're adding heat in order to get it from 25 degrees Celsius to 100 degrees Celsius. And then it begins to boil. And as we add heat, now all that energy is going into changing the liquid water to vapor water. And you can see that the temperature does not change during that process. All right. So let's take this diagram and apply it to our energy bar charts. Okay, so we're going to do this in separate charts. So what I'm going to do, I'm going to call this stage that LOL diagram, and this next stage is going to go on the next page. Okay, so let's work through this first stage right now. Okay, again, we've got liquid water to start with, and we're at about room temperature. So this is room temperature, 2 bars. We've got liquid water, that's 2 bars. Okay, we're ending this first part of the process at high energy, and we're going to go to 100 degrees Celsius, and we're going to go to 4 bars. That's a big increase in ETH, thermal energy. So far, we have not changed the phase. So phase change, there is no phase change yet. Okay, EPH is the same. Now we are adding energy, of course, right, to the system. And according to our diagram, we added 2 bars of energy. All right, well, that's our the first part of this process. Now let's work at the second part. Okay, the second part is on the next page. Okay, so here we are, second page, and we are going, what we're at, we're starting at 100 degrees. This is the second stage, right? We're at 100 degrees Celsius. ETH is 4 bars, just like it was before, because we're picking up where we left off, right? And we were at liquid water. That's 2 bars, okay? We're still adding energy to this, right? We're still adding energy, and this water is boiling. The temperature does not change. It stays at 100 degrees. That's still 4 bars of thermal energy. But the EPH now, since we're going from a liquid to a gas, we're going to stick to the rules that we established, and we're going to say gas phase is 4 bars. Okay, so what are we adding to this stage? We are adding 2 more bars of energy. Altogether, I mean, just saying, altogether, the first part and the second part, adding them together, that's a total of 4 bars of energy that we're adding to this in order to make it happen. All right, I love this question. This next question here. You may have wondered in your life, why does water boil? You know, why do we get these bubbles forming? And when water is boiling, it's really, we're forming these bubbles vigorously, right? You've seen water boil really hard, right? When it's really boiling fast. We've got bubbles of water, bubbles of water, bubbles of water forming. What is that? What's going on there? And I think we know enough about chemistry now in this class to really figure out what's happening there, okay? And in this question here, we're being asked to draw a particle diagram of what's going on in that boiling water, okay? So we're going to start with, I'm just going to draw a particle diagram. We're starting with liquid water, so I'm just going to draw a bunch of water molecules everywhere, okay? All right, so there's my liquid water. I've got a bunch of water molecules. They're close together because this is a liquid. They're all running around like crazy, and they're bumping into each other, and obviously there's a lot of energy going on there, right? A lot of thermal energy, very fast-moving particles. What's going to happen eventually, you can imagine that these particles are going to start separating from each other because there's so much vigorous motion going on around here, and there's energy being added to this. we're going to be separating now these particles from each other. We're separating these particles, and we know what that means, right? We know that we're forming a gas now. So I'm going to draw another diagram showing now a bubble of water vapor forming in this hot water. Okay, there's my bubble that's formed. Inside that bubble is gas water, in other words, water vapor. And you know that if I'm going to draw water vapor, I'm going to draw particles that are very much separated from each other. Okay, so we've reached the boiling point with this water, and suddenly we get these pockets of vapor forming within the liquid water. We get these pockets of molecules that have been separated from each other, okay, because of the energy that we're adding to the water. We start with no bubbles, okay, but then after we've added enough energy and we start separating these particles, they start to separate from each other to form pockets of water vapor. And then that water vapor is going to, rise to the surface because it's less dense than the surrounding water. What we've got here is boiling water, if you ever wondered how that happens. But it would be very helpful for you to draw this, write this in your notes, showing, this is what happens when water boils. Okay, so what is inside the bubble? Well, it's water vapor, particles of water that are separated from each other. Why do I think so? Because I'm the teacher. And I know, that's not the answer. It's because, how do I know? Because I know the nature of gases. You know the nature of gases. We know the nature of liquids, okay? We learned that in Unit 1 of this class. We learned the difference between a solid and a liquid and a gas based on density. And gases are much less dense than liquids because the particles are separated by a lot of space. All right. Okay, looking at number 5. I'm not going to write anything down for this. I'm just going to talk you through this. But I hope that after seeing the demonstration that we did in class, I showed you boiling water, and at the time you were like, yeah, so what? Well, anyway, I did that for a purpose because I wanted you to see that the temperature of the water did not change while we were boiling the water. And it doesn't matter how much heat you add to boiling water, you are not going to change the temperature of that water boiling. Okay? If you add more energy to water that is boiling, the water is just going to boil faster. It's not going to change in temperature. Okay? So I'm not going to write that down. You should write that down in your notes. All right, here we are on problem number 6. And this is showing the heating curve of a liquid. So far, all we've ever done was look at water. Any other liquid is going to have a similar kind of a heating curve. Let's just look at this heating curve. First, let's interpret this, all right? Let's not just answer the question here, but let's use this opportunity to really look at what we're seeing, or to think about what we're seeing. Okay, so here we are. I'm going to draw some things here, but here's our heating curve for this liquid. Over time, we're increasing in temperature during. I'm going to separate this into numbers. So during part 1 of this graph, we're going from a cool liquid to a hot liquid, okay? And during part 2 of this graph, we're we're taking this liquid and we're turning it into a gas. So during this time, right here at about where I'm pointing my laser pointer, we've got nothing but liquid water, liquid, whatever liquid this is, okay? So it's liquid. But during this time, we are going through a phase change. We're going from liquid to gas. Okay? And as we proceed, we're turning more liquid into more gas, more liquid into more gas, more gas, more gas, more gas, until we have nothing but gas. All right? At the end of this process, in part 2, we've got nothing but gas. Now, in this last part here, part 3, okay, in part 3, we're going from, it's all gas, and we're just now increasing the temperature of that gas. All right, I'm going to say these words again. Part 1, all liquid. Increasing temperature of the liquid, increasing the temperature of the liquid, increasing the temperature of the liquid until we reach the boiling point. And now, and I'm going to write that. If you can't read that, I'm going to say these words. I'm sorry for my handwriting. So right there, this point right here, this temperature, it's a temperature. This temperature is the temperature at which this liquid boils. It's going to boil at this temperature. And notice that this temperature is the same all the way across. Okay? All right. After we've boiled all the liquid away, the liquid is now all gas, and now the gas is going to increase in temperature. And really, that gas could increase in temperature for a long, 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 long time. Okay? All this time, we've been adding energy with time. Okay? All right, let's just answer this last question here. Sketch the heating curve for a larger sample. Well, what if we had a larger sample? Let's really think about that. I mean, if we had a bigger sample, do you think we would change temperature as quickly? Imagine this. It would probably take more time to increase the temperature if we had more stuff, right? So here, let's keep a couple of things consistent. We're going to say the boiling point is the same. So the boiling point is going to be the same all the way across there. The boiling point of this material is not going to change. But the rate that we heat it, if we have more stuff, it's going to take more time to heat it up to that boiling point, right? So this is going to take more time. I'm going to make that really super obvious. So we've got a larger sample, right? It's going to take more time. The heating curve is not going to be as steep, and it just takes more time to get to the boiling point. And then once that happens, well, now there's a whole lot more stuff to boil, right? So that's going to be a lot of material to boil. And I'm going way off the charts here, but I want you to see that more stuff, that means there's more to boil, so that's going to take a longer time to happen. But the temperature stays the same as it's boiling, okay? And then once we boil everything away, and now we're all vapor, then we can increase from there. So that would be the difference between having a little bit of material and a lot of material, okay? And then, all right, let's do that. Just quickly, of course, for number 1, that means all liquid. At number 2, we've got liquid and gas. Liquid is becoming gas throughout that entire number 2 process. And then at 3, we've got nothing but vapor or gas, okay? So during part 1, it's all liquid. During part 2, it's liquid and gas, right? Depending on where we are in the boiling process, we start out with all liquid, we end up with all gas during that boiling process, and any place in between, we've got, a mixture of gas and liquid. And then during part 3, it's all gas. Okay, I hope that's clear to you. And then just talking through what we already know about the difference between liquids and solids and gases. In the liquid phase, the particles are close together and moving around each other. We know that. We've known that for a long time. During part 2, the liquid and the gas, we're really going to see a lot of this going on, right? During that time, we've got bubbles of vapor forming until we run out of liquid altogether. Okay, so that's what we're going to see there. And for the gas, of course, that's particles separated from each other by a lot. Okay, I think we've answered all the questions there. Thank you for sticking with me. The more you watch these videos, the better you're going to do with an assessment, be it the part 3, a unit 3 assessment, and the semester exam that's coming up. The very last part of this, label which phase or phases of the substance is present at each of the 3 portions of the heating curve, and describe the arrangement. Okay, so, and the